Hey everyone, in this video we are looking at centripetal force. We are actually kind of going back and applying the basics of Newton's second law and how we evaluate and apply forces and net forces to things for objects that are moving in a circle. And this is of course going to be applying what we learned before, all about centripetal acceleration. That plays a large role. So to start off, all right, going just way back to Newton's second law. Well, we know that Newton's second law says the sum of the forces acting on an object is equal to m, the mass of the object, times the acceleration of the object. Okay, it's as simple as that. Well, I can apply that for things in circular motion because we know that things moving in circular motion, their acceleration is c, the centripetal. Okay, if you need to, as a reminder, that's the centripetal. That's the term, acceleration. And we saw that centripetal acceleration is equal to v squared over r. Okay, the speed of the object, that tangential speed squared, divided by r, the radius of the circle. Well, that means that I can rewrite Newton's second law as this. So the sum of the forces is equal to m times a, and this is the centripetal acceleration. So instead of just writing ma, I can write m v squared divided by r. So this term here is the new sum of the forces. So since we're using centripetal acceleration, oftentimes I'll do this, put a little c right there. So the sum of the forces, this centripetal force, okay, is mv squared over r. This whole thing is what we call centripetal. Centripetal meaning center seeking. Centripetal force. Okay, this whole term here on the bottom. All right, some things about that centripetal force. So on my next slide, I'm actually going to redraw my little c right here. Oops, not right there. Right there. So that's centripetal force. Well, MAC, mv squared over r. Okay, the centripetal force. I'll even write it down again, just so I remember. The centripetal force is that force, the net force, required to keep something moving in a circle. This is our key definition, what centripetal force is. It's the net force required to keep something moving in a circle. Because of this, what I just underlined, the most important thing to remember is this middle bullet point, the most common misconception. Centripetal force is not a new force. It's not like tension or weight or friction. Okay, all of those were individual forces acting on the object. Centripetal force is just the new way we are writing the net force. Instead of saying the sum of the forces equals ma, the sum of the forces equal mv squared over r. Okay, the sum of the forces, when you add them all up, they give you the centripetal force, mv squared over r, f little c. Okay, and because we saw that the centripetal acceleration is always pointing toward the center of the circle, and by Newton's second law, the net centripetal force always points toward the center of the circle. Okay, we always know what direction it's going to act. If something is moving in a circle, it must mean there's a centripetal force, the net force, okay, and it must be acting towards the center of the circle. And just to highlight this point again, we're going to be drawing free body diagrams. We're never going to draw like this. Okay, here's an object. There's that dot for FBD. Oh, and here we go. That's FC. We are never going to see that. And if you draw that on a homework or test or something, it's going to be incorrect. We're going to draw our free body diagrams like we usually do, labeling known forces, weight, tension, etc. Okay, but when we add them all up, if that object is moving in a circle, we set it equal to the centripetal force, the new net force. So here I have kind of a classic diagram. I have someone who's standing holding like a ball on a string. and they're twirling, they're swinging that ball around in a circle. And I have this side view of the individual, and then I have like a top-down view of her as she's swinging the ball around. Okay, so just focusing on this spot right here, let's say that the position of the ball at this moment here is A. Okay, the tangential velocity at any point would be tangent to the circle. So it would be something like that, tangent to the circle. That would be V. We know the centripetal acceleration should point towards the center, and the centripetal force, that's what this green arrow is, should point towards the center. This is the direction of the net force. In this case, it's a tension. It's the tension in this string. All right, we are going to look in the next slide of an example of how to set this up. I want to highlight something that we're really not going to be saying in this class, and that's the more commonly known term outside of physics, centrifugal, also pronounced that way, forces. Okay, we are not going to be using the term centrifugal or centrifugal forces. Okay, some people say that centrifugal forces aren't real and they don't exist, and that's not really true. It's all about our reference frame. When we've been looking at objects, whether it's a block just moving across a flat surface, going down an incline, looking at collisions, whatever, we've always kind of had this bystander reference frame. We've been outside of the motion. We're not in the block while it's going down the ramp, for example. We're kind of on the outside watching the block slide down the ramp. We're going to keep that same reference frame. So like the reference frame in this picture, we see the girl, she's swinging the ball in a circle, we see the ball moving in a circle. In this reference frame, we will always be using centripetal forces. Okay? Centrifugal is if you take a rotating reference frame, if we were inside the ball, okay, and we were experiencing or we were trying to notice what forces are acting on us as we're being whirled around, then the term centrifugal force would be appropriate. Likewise, if you're in a car and someone like cranks the wheel to the left, right, it feels like you're thrown against the side of the car, then you could talk about this term centrifugal. Okay, but because that's not the frame of reference we're using, we're not going to be using this term. Not that it doesn't exist, not that that's a fictional force, it's just not a force that's in our reference frame from this outside. Okay, the last thing right here is a very common question and a very real experience. If you're swinging this ball, you feel the ball tugging on your hand. Okay, or in the second diagram here, if the string was to snap, the ball is not going to keep moving in a circle, it's going to follow this trajectory here. But that's not because of a centrifugal force pulling it away from the circle, it's really just the inertia of the object. Remember, things like to keep moving in a straight line. So to prevent that object from moving in a straight line, there must be centripetal forces curving it inwards towards the center. And if the string breaks and there's no longer that net toward the center force, things are going to follow inertia toward their straight line motion. Okay, all right, last slide. Finishing things up with an example. How do we apply Newton's second law? I have that same picture. I've just kind of made it smaller. I cut off the right side. Same thing. Girl's moving the ball around to the right. I'm again going to call this point here A. Normally, when we try and approach and we try and apply Newton's second law, we would start with a free body diagram. We're going to do the same thing. Free body diagram for the ball. Just to make it clear, it's the ball. So it's this little dot right there. So I make a dot for my object. Two forces are obviously acting on it. There's the weight of the object, okay, Fw, and that equals mg if you forgot. And there's another force. There's the tension from this string. And tension always acts along kind of the string itself, at least how we use it in our class. So in this position here, that tension is moving to the left. So I'm going to try my best to draw a straight line. I'm going to call that T, T for tension. You might think, okay, well, what about when the ball gets to this other side? Well, then our free body diagram changes. So it might be worthwhile to make it really clear where you're applying, where you're drawing that free body diagram at this point A. Another thing, we would always choose direction. Which direction is positive, which direction is negative. Okay? Well, since this object is moving in a horizontal circle, saying left is positive or negative is going to be confusing because, well, the object is moving around and around and around. Sometimes this tension force would act to the left, sometimes it would act to the right. So you might have to change plus to minus in some cases, minus to plus. We're going to change our convention. We are going to say that toward the center is one direction. And I usually say that's positive. So away from the center would be negative. Right? Because this object's moving horizontally, I could still say my usual, oh, let's say up is positive too. Okay, but now slightly different, but at least this will always be consistent. Towards the center will always be positive. Tension is always going to be acting towards the center. Away from the center, if there are forces, could always be negative. So let's set up the sum of the forces. We can choose our direction. Let's look at forces acting towards the center. So not so much x, that kind of loses meaning. Let's look at forces acting in the centripetal, towards or away from the center of the circle. Well, mg is not acting towards or away. Towards or away is either this or this. mg is acting perpendicular. So just like we wouldn't include that in the sum of the forces in the x, we're not going to include it in the sum of the forces in the centripetal. There's only one force, and that's tension. Tension is always acting toward the center, even when the ball's over here. Because when the ball's over here, tension must act this way, towards the center. So that will always be positive. I don't have any other forces. That's equal to MAC. And I know that AC is M, or AC is V squared over R. So here's my equation. T equals mv squared over r. I know I didn't give you any numbers, but if you're trying to get an expression for the speed of that object, just solving for that tangential velocity, that would equal, well, swing that r over, I'd have t times r divided by m, and then I'd have to take the whole square root of it. Okay, so this here is the key. We're going to set up Newton's second law like we usually do. We look at all the forces acting in a particular direction, set them equal to ma. But now our direction will include towards or away from the center. This is kind of taking the place of our x direction, at least in this example. And when we add up all the forces, we set them all equal to mac, or mv squared over r. Again, to highlight, I did not add like fc. Centripetal force is not an individual force, it's what all the forces add up to. Just like in regular motion, all the forces add up to ma. Here all the forces add up to mv squared over r. Okay, we'll be getting practice with that. Thanks for watching.